Right. So I'm very pleased to welcome this week's Colloquium speaker, Jack Singal. So Jack did his undergraduate work at NYU, and then he completed his PhD at UC Santa Barbara, working with Phil Lubin, who was recently visiting here to talk about SETI. He then did postdocs at Goddard and at Stanford before moving to the University of Richmond as an assistant professor in the physics department. So Jack has worked in many different areas, ranging from hardware development for the LSST to multi-wavelength studies to determine cosmological evolution of quasars and blazars, and we saw some of that in his lunch talk. Today he'll tell us about an interesting puzzle, which is a faint isotropic radio background which has been detected between about 20 megahertz and 8 gigahertz, and he'll discuss some of the proposed origins for this cosmic radio background.
Hey, thank you, Michael, and thanks for having me here. So, starting out on the cosmic radio background, let's have some background information, pun intended, on the rest of the photons in the universe. So, we're all familiar with the cosmic microwave background from last scattering. The cosmic infrared background from thermal dust emission in galaxies, the optical UV background from starlight. The cosmic X-ray background is mostly AGN, but maybe other stuff. And the cosmic gamma ray background, AGN, star formation, and possibly other stuff. And it's very reasonable to ask what happens if we go over this way. Well, interestingly, a monopole component of the diffuse radio emission was identified as early as the 1960s. And of course, monopole here means isotropic over the whole sky, which is what you would expect from a background. These papers were the ones that reported that. These were from those days of radio astronomy. But they passed, I think, somewhat unappreciated. By the 80s, the results from the Haslam survey, which is kind of the gold standard in an absolutely calibrated radio map of the whole sky, 408 megahertz, was clear about the existence of a radio monopole in these papers here. Again, it passed without a lot of notice. So now let's have a discussion of how we would measure such a thing. Well, at the frequencies in these megahertz range of these surveys, the way you would do it is with an absolutely calibrated single dish radio map. Now that absolutely calibrated part is important. Most of the time in radio astronomy, especially interferometry, there's no determination of the absolute level of the sky. It's just looking at points that stick out relative to other points. You actually have to be really careful if you propose to do an absolutely calibrated measurement where you can say this number of counts corresponds to this temperature. I'm going to put up now a chart of the frequencies and the strength of this monopole signal. And you can see that when we're in the low megahertz range, it's enormous. And therefore, huge uncertainties are okay, because you can pick this signal out even if you have a huge uncertainty. As we come into the gigahertz range, this signal is small. This is on top of the CMB. So this is a small signal, and therefore this uncertainty has to go way down. So when we're in the gigahertz range, we need to do something other than a single dish radio measurement. So how to measure it at the low end, I'll tell you that in a second. First, let's have a reminder that in this region, if we're talking about, say, a gigahertz and around there, there's a lot of things competing on the sky. We have the cosmic microwave background here, 2.7 Kelvin. Just for reference, this here is the level of CMB anisotropy, 4 orders of magnitude below. And we have the diffuse radio glow in the galaxy from synchrotron emission. We all know synchrotron emission is from the high-energy electrons spiraling in the magnetic field, and the free emission as well. And the signal we're looking for basically looks like this on top of all of this stuff. So to make that measurement, and remember now I'm talking about at frequencies where we need a very low uncertainty, that's going to be from this instrument here, this project. So ARCADE stands for, it's an acronym, Absolute Radiometer for Cosmology, Astrophysics, and Diffuse Emission. We don't need to know that. As you can see here, it goes on a balloon to the upper atmosphere. We have to do that because when we're trying to get millikelvins of uncertainty, the atmosphere matters because the atmosphere emits at a few millikelvin. So getting above the atmosphere is important. So high altitude balloon to the upper atmosphere. This little thing here is the experiment itself. Here's a blow up of that. It's kind of like a giant beer stein, and the lid comes off just like that. Now, when that comes off, if you had X-ray eyes and could see in there, you would see this. So we have here horn antennas, which couple the radiation from the sky into the radiometers. And on top of it is this structure here, which rotates like a lazy Susan on a table, so that these horns can either look out through this hole at the sky or at this thing right here, which is a black body emitter of known and adjustable temperature. And we can look at the sky, then look at the emitter, and adjust the physical temperature of the emitter until the signal from the sky matches the signal from the emitter, and that tells you the temperature of the sky, nulling out all the uncertainties and differences that come with the imperfections back here. So this will achieve millikelvin level absolute uncertainties from 3 to 90 gigahertz. As I said, the radiation from the sky is compared to this external black body calibrator. We adjust the calibrator temperature until the radiometer thinks it's seeing the exact same thing as the sky, and that's the temperature of the sky. The systematic errors here are minimized by, okay, for one thing, this is all open. There's no windows up here, which of course emit and absorb and do weird things in the microwave. So we're looking directly at the sky, and we're keeping everything cold at basically the temperature of liquid helium at 0 pressure. And so, therefore, all these things are the temperature of the background or lower, and so they're not emitting appreciably compared to the sky. So now just a few fun kind of instrumental things. There's one instrumental slide here. So the primary challenges / innovations here are, one, as I just said, maintaining and controlling these very cold cryogenic temperatures at the top of something that's hanging from a balloon at 120,000 feet, and the blackness of this microwave calibrator, because something to be a black body needs to have no reflections. So, first of all, the thermal control. The way we do that is with a so-called superfluid pump. The way this works is we have a plumbing fixture here and a ceramic plug on this side and a heater on this other side, and these sit in the liquid helium that's at the bottom of the dewar. Up at 120,000 feet, the pressure is low enough that the liquid helium is below the superfluid transition temperature. So it's a superfluid. Superfluid likes to flow, so it can go through this ceramic. It gets in there, and then it gets heated into the normal helium phase. When it's in the normal helium phase, it can't get out. So superfluid goes in, but it can't get out, and so it pushes the helium up, and it's like a fountain. And we can move helium up 10 feet up to the top of the dewar and just kind of dump it all around this fountain, spraying it all around on the things that need to be kept cold. As for the blackness of the calibrator, it is one of, I think, the blackest microwave object ever constructed. It consists of this, a bunch of these very pointy cones of a particular material. It is die-cast black epoxy loaded with stainless steel flour, if you care to know. And there's about 300 of those. This is a close-up, but the important thing is that some of them have thermometers embedded in them, and that's how we're reading out the temperature. This core here of aluminum and this little copper wire helps maintain the isothermality of these cones. And here you can see the reflected power off of these. Remember I said, and we all know, that to have a black body, you would have 0 reflections. Well, you can see at some of these frequencies, the level of attenuation here, right, of reflections. It's basically photons will go into this thing and never come out. And you could picture yourself as a microwave photon about this size, and you can get impaled on this structure, basically, right? So then,
what is the impedance compared to free space?
of the material here, you mean?
Square.
Sorry, of the material.
Yeah.
So there's a very complicated dielectric constant with an imaginary part, and it's a pretty technical thing we could talk about. Okay, that was one instrumental slide. So skipping over a bunch of important stuff, when you measure the sky, the results are this. Okay, so from 90 gigahertz to 3 gigahertz, this is the CMB, cosmic microwave background, and we see the clear rise above that, where the radio background is starting to take over. And then when we combine it with those megahertz radio surveys I was talking about, we get a pretty consistent power law over these decades in frequency. So this here is the temperature of the monopole component, the isotropic component of the radio sky. So it's a power law. We recognize this index here as what type of emission? Anybody? 2.6. What process? Yeah, not for synchrotron. I heard somebody say. Yeah, that's very typical of synchrotron emission in temperature, radiometric temperature units. It would be 0.6 in photon density. And so there it is. So you can see that at 1 gigahertz, we're at about a Kelvin. So now I want to summarize where we've come so far. The absolutely calibrated single dish radio maps at megahertz and the arcade experiment at gigahertz is telling us they agree that there's a significant radio monopole 4 or 5 or 6 times brighter than was expected in the past. The radio emission has a synchrotron-like spectrum. And it's isotropic on greater than 1 degree scales, because that is the scale of these radio maps. Okay, so in bold now, there is a significant radio monopole. The only question is whether it is in the galactic halo or extragalactic, or maybe something else that you want to propose. But it's there. That should be uncontroversial. The question is, where's it coming from? And of course, you can't tell the difference just by looking out, because if something is coming from beyond us, and it's all over the sky, we don't know if it's coming from the local neighborhood, the galactic halo, extragalactic, cosmological. So the rest of this now, I want to address what is this strange isotropic radio emission. So I want to show several limitations that we derived in this paper here. The first one is the inverse Compton question. So let's remind ourselves that the synchrotron emissivity is a combination of the electron energy density and the magnetic field strength. Up the electron energy, you get more synchrotron. Up the magnetic field strength, you get more synchrotron. So for a given synchrotron level, if we take the magnetic field down, then we have to up the electron energy to get that level of radiation. But more electron energy means more upscattering by inverse Compton radiation of the other photons that are around. What other photons are around? Any ideas? All over CMB. Okay, so we have a limit that we can't inverse Compton the CMB into X-ray and gamma ray more than the observed X-ray and gamma ray backgrounds. So here is all of the backgrounds, CMB, infrared, optical UV, and the resulting inverse Compton signal for different magnetic fields where the synchrotron comes from. If we make the magnetic field go down, the electrons have to go up, and we have more inverse Compton. So clearly this all violates observations, and so the magnetic fields need to be microgauss or higher. Nanogauss is not going to do it. Okay. Consideration number 2. if we have a sum of discrete sources to make this background, there has to be a whole lot of them at low fluxes because we've already counted up all the higher flux objects. You go out, you take interferometers, you do surveys, and you count up all the little point sources. And the ones that we've already counted up actually already get us to about a fifth of this radio background. So radio source counts, if you plot them in strange units, they look like this. So if something is sloped upwards here, you're getting more integrated emission as you go down to lower fluxes, right? Because you're always getting more objects as you're going down to lower fluxes, but you have lower fluxes. So if you get enough more objects, you're okay. But what radio source counts tell us is that we see large radio galaxies, we see the start of the bulk of quasars and ordinary galaxies, and then we run out. This is the limit of interferometer surveys now. Now, they all disagree a whole lot about what's happening down here. If we're getting a lot more objects down here, we could form the radio background pretty fast. If we're not, we can't. So as a function of the slope, the power loss slope of this end here, how many objects do we need? Well, at the most optimistic, high slope going up, we would need about 10 to the 11 objects per steradian. But it gets rapidly worse than that, okay? And already at 10 to the 11, we're kind of at all the galaxies. Here's another limitation. Okay, all the galaxies, you could say, well, how about just all the galaxies? Well, we have in the local universe the radio far infrared correlation, which many people know about. Nice relationship between the far infrared emission and the radio emission in ordinary galaxies in the local universe. Well, if this trend applies to all galaxies all throughout the universe, then you could multiply this correlation by the radio background and you'd get way too much infrared background. So the sources that are making the radio background cannot follow the local radio far infrared correlation. So that places a lot of limitations on some sources that would be outside of our galaxy. Let's look at the bright side of that suggestion for a second, though. The case for extragalactic origin. If the radio background is from galaxies, we would need the radio far infrared correlation to evolve with redshift by about a factor of 5 to redshift 1. Conveniently, right after this result, it was measured to evolve by Blast and Herschel, but not quite enough, but some. And this is a very tough measurement to do because it's affected by all kinds of biases. I'd like to give an honorable mention to these papers, which reach the general consistent conclusions that I just went over. Let's do the case against an extragalactic origin. Many problems with that. Okay, so one thing is those source counts. Remember that if that slope is going up, we need all the galaxies in the universe. If that slope is going down, not even all of the galaxies in the universe can do it. So what about those? So some people go into the infrared source counts, apply the radio far infrared correlation to get a predicted radio source counts. And those do not give us enough sources. So these papers did that. Or there's any hardcore radio astronomers in the room? Anybody? So there's what's called the P of D analysis. So to do a two-penny injustice to this, in a radio interferometer map, the deviations you see in all the pixels from 0 is the places where there aren't sources, is a combination of all the sources that are too dim to make your catalog, but are there, adding up in the background, plus the noise. And if you have an estimate of what the noise is, you can back out with your observed map and all those deviations what the underlying all the too dim sources are in that map. And so these, if people know Jim Condon, these are very serious people, and they think they can do this with their radio maps and say that if there's a bunch of sources in there, they're really dim. And if they're really dim, we need a ton of them. to make the radio background. So here are some models that would make the radio background out of very dim radio sources. Okay, but these would be at nanojanskis and tens of nanojanskis and just a whole ton of them. So that would require an entirely new population. Here's another problem. There are observations with certain interferometers of the anisotropy of the radio background. Now remember, interferometers cannot see the radio background because they're insensitive to an overall level. But they can see fluctuations, and they've measured those fluctuations to be below these, or they've put upper limits on them, below these values here. Then you can go in and say, if the radio background is made from a bunch of sources, and those sources trace out the dark matter halo distribution at low redshifts, what would be the expected anisotropy that you would get? Because we know what the dark matter halo distribution looks like on angular scales. And this is what it would look like if it was redshift 0 to 1. And that over here is more anisotropic than the limits that these interferometers have observed. This is, and now of course if you do this, if you sum up sources at different redshifts, it washes out some of that clumpiness. So this is if it's redshift 0 to 2. This is if it's redshift 5. That's getting a little better. The other thing is if the sources are larger, then they start to overlap, and that suppresses this anisotropy. So if the sources are about a megaparsec in characteristic size, then the expected anisotropy would go like this, and that would not violate these existing measurements. But this is a pretty strong thing that says that just a bunch of galaxies would be problematic. It would make too clumpy of a radio background. This paper here, these folks looked at some high redshift mechanisms, because high redshift is okay, and said they couldn't do it with a cosmological injection of photons or electrons. So if all of these extragalactic explanations are running up against rocky shores, what about putting this signal in the galaxy? Well, these authors came up with a model, a rather simple model, of two components of galactic diffuse emission, a disk and a round halo. And they fit the observed galactic emission, which has, a pretty big plane component and this isotropic component we're talking about. And they fit that to different size halos and disk at different frequencies and with different spectral indices in these two components and all this kind of thing. And we're able to reproduce the observed maps by having a huge galactic halo of radio emission surrounding us. If people are familiar with the Galprop effort, they are tracing the distribution of cosmic rays and magnetic fields throughout the galaxy, and they are kind of in this business too, and they can reproduce the same thing with a giant halo of emission coming from 10 kiloparsecs above and below the plane of the galaxy of cosmic rays flying around. So, does our galaxy have a giant halo of electrons and radio emission and magnetic fields? Well, here's the case against that. So first, we have the same inverse Compton problem. Because around our galaxy, we don't only have the microwave background, we also have a lot of optical and infrared light from our galaxy. And we kind of have a measurement of the magnetic fields in the galactic halo from rotation measures. And so this seems like it would also produce a giant X-ray signal that's not seen. The other thing is that the large-scale galactic radio emission is well fit by simple models that vary with galactic latitude and don't give a giant halo. And simple is good. And then we have a nice detailed effort of modeling the cosmic ray propagation and the magnetic fields to come up with the synchrotron structure of the galaxy, and they don't see, they would not say that this giant halo is there. But we can do something else which is see whether galaxies similar to ours have this giant round thing surrounding them of radio emission. And so that's these results I'm going to talk about here. Now, if we're looking at galaxies to see if they can do this, for one thing, they have to be close by because faraway galaxies are just a point in radio or any other kind of light. But close up, you can see the structure and map it out. And then the other thing is we need a galaxy that is edge on, right? Because if you're looking at the disk, the underside of the disk, it's round anyway, no matter what. If we flip it so that the disk of the galaxy is here, then you can see if there's a giant halo above and below. So we need galaxies that are close by and edge on. And there are radio emission contour maps of galaxies that are close by and edge on. Here's an example. So the question is, do they have a shape structure, which would be a round halo on the outside, round out here, that would be predicted by this model? Well, here is what happens if you take that model and observe it, so pretend it's a real galaxy out there, and observe it with different size radio beams. So this is like a point spread function if you're familiar with optical astronomy. In radio, you have a beam size. Well, a small beam doesn't smear things out very much, and so you get a nice clear map. And so if we have a small beam, this is what the contours would look like in that model, if that model was a real galaxy, at different temperatures. So the 1 Kelvin hot is clearly in the disk component here. But the 0.1 Kelvin is clearly in the halo component. So if we look for the 0.1 Kelvin contour, if it's round, that's telling us there's a halo. What if you have a big beam that smears things out? That's no good. That just takes all the heat from the center and puts it to the edge. And so no matter what, it's going to look round. So we need observations that are nearby, edge on, and small beam. And there's not that many of those. So contours that are at 0.1 Kelvin or below can distinguish the presence of this halo if the beam smearing is small enough. This is basically all of them. This is all of them. This is all of the nearby, edge-on, small beam radio maps of galaxies. Now, we can do two things. We can do an absolute level comparison between contours. So compare the contours in these maps at the same absolute level as the one in the model map. And remember, in the model map, the one that tells us the halo is there is 0.1 Kelvin. So all of these are contours around 0.1 Kelvin. Or we could say, what if these galaxies just scale up and down in brightness? Then you wouldn't necessarily want the 0.1 Kelvin. You'd want the one at that same fraction of the peak brightness. So that would be this, a fractional level comparison. Compares the contours in the observed maps to the contour at the same fraction of the peak brightness in the model map. Now, we can go in and measure the contours, how elliptical they are or round. How do you measure? What's a measure of ellipticity? The axial ratio, the major axis over the minor axis, -1. So small axial ratio is round, and big axial ratio is elliptical. And how do you measure the size of these contours on a radio map? With calipers, literally. So here's the results. This is, again, all of the nearby edge-on spiral galaxies with a small beam. The white points are the actual galaxies and their axial ratios, big, elliptical. The solid histogram is where the model predictions for all these galaxies should be. Round, small axial ratio, round. And this is on the absolute level, and the comparison, this is a fractional level. So again, the absolute comparisons are insensitive to any structure in the plane, because we don't care, we're just looking at the 0.1 Kelvin contour. but they're potentially sensitive to the normalization of galaxy brightness. Super bright galaxy, super dim galaxy. The fractional contours are insensitive to the normalization of brightness, but potentially sensitive to structure in the plane. But neither of them show anything like the real galaxies that are out there. So galaxies similar to the Milky Way are way more elliptical than this model with the giant halo, disfavoring the huge round radio halo. So what if we tried to modify it to fit the observed data? We'd have to dim the halo by a factor of 4, which would place the isotropic signal in some non-halo thing, and we're just back to an extragalactic signal. So when our galaxy doesn't work and other galaxies don't work, people start fishing for more exotic explanations. What's the go-to exotic explanation in astronomy? Okay, local's not so exotic. Just in general, in astrophysics, the go-to exotic. Yeah, I heard it. Dark matter. So, annihilating dark matter. So in this paper here, for Nengo and others, they say, what about all the filamentary structure all in the cosmic web? What if you had dark matter decaying into electrons and positrons for a synchrotron? The magnetic fields probably are not high. They need higher magnetic fields than probably exist out there. But it's an interesting suggestion. This paper here talks about if we have the dark matter annihilating to electrons and positrons in substructures in the halos, depending on how clumpy the dark matter is, it would evade that smoothness problem because the emission structures would be greater than megaparsec scale. It requires large substructure in the halos, like I said, unless they have this reacceleration of electrons due to the turbulent waves in the intercluster medium. So that's an interesting suggestion there. Here's some really exotic things: quark nugget dark matter and dark stars. Here's another good one: cluster mergers. So we have turbulence when clusters merge, so that accelerates electrons and amplifies magnetic fields. They think they can get 4 microgauss magnetic fields, which is good for this. Gets around the inverse Compton problem. And the sources would be large. Great, because clusters are big. So we get around the smoothness problem. Here's a particularly fun explanation: the population 3 supernova from this paper, Bierman et al. So what they do is they just say, what if we're going to make the radio background from all the supernova of the population 3 stars going off way into high redshift? And we'll say, what rate of population 3 supernova do we need for that? And the rate they get is exactly the rate that gives us the observed supermassive black hole abundance in the universe. This evades the constraints discussed so far, at least most of them. It's high redshift, so we get around smoothness problem. There's no radio far infrared problem because there's no dust at the very high redshifts. The sources are further extended because of the way the angular diameter distance goes. You know, when you go to high redshift, if you go angular diameter distance, things get smaller and smaller and smaller, but then bigger and bigger. So the sources are bigger and extended, and that has 2 effects on the smoothness. One is that the sources get wider than the interferometer beams, and so when they're wider than the interferometer beams, they don't contribute to the clumpiness, the observed clumpiness. And they start to overlap, and so for both of those reasons, the P of D analysis that tried to get all those source counts would just miss these sources, just kind of adding all on top of each other in those radio pixel maps below the detection flux. This result does disagree with the simulated rates of population 3 supernova from the hydrodynamic codes of, for example, Wise and Abel. I did ask Bierman about this, and he said that he thinks it's better that his rate matches the observed supermassive black hole abundance, and he would believe that over simulations. So here's that first plot I showed, but now with the radio background added with the other backgrounds. So you can see its relative importance in energy density units. And this morning, we decided that something that is about 10 to the minus 5, the energy density of the CMB, is interesting. That something was the binary black hole merger gravitational wave background. Well, here's another thing that is 5 orders of magnitude below the CMB energy density in the universe. So if you're interested in one, you could be interested in the other. So to conclude this then, slightly early, the radio sky has a bright isotropic synchrotron component, which is either galactic or extragalactic. I know, profound. It must originate from regions of relatively high magnetic field strength, microgauss or higher. It must come from sources that differ from the local radio far-infrared correlation. The sources must be either at redshift greater than 5 or not trace the large-scale structure distribution or be extended to about megaparsec or larger scales. Synchrotron from population 3 supernova is an intriguing possibility. If the signal is galactic, it must either be from the halo in places with a strangely high magnetic field, or more, I didn't talk about this, but if it's more local in the galaxy, it would have inexplicably low polarization. And if galactic in the halo, the Milky Way galaxy would be quite anomalous, actually completely unique among all of the observed normal spiral edge-on galaxies. I believe that is it.
Okay, so questions for Jack?
Okay. After much sound and fury, it turned out that the quarter keV X-ray background comes largely from the heliosphere.
Yeah.
Is there anything in the heliosphere that could do that?
So the problem we would have with the heliosphere or the local bubble is that if we have a very local high density of energetic electrons making synchrotron, the local magnetic field structure of the galaxy is very regular because we're not averaging over many domains to make it irregular. So magnetic field lines pretty consistent all around this local region. Then that would give rise to highly polarized synchrotron emission. And that signature ought to be seen in WMAP and Planck. And we don't see this highly structured, polarized emission all surrounding us in those maps.
So interplanetary magnetic field voltage polarities.
On what scales?
AUs, less?
Oh, really?
Yeah.
Well, we should talk about that then. So that's a good suggestion. Yeah. Okay, that's a good suggestion then. The more what I said then applies to the local bubble region of the galaxy where you would have very, very regular. So we should talk.
Other questions?
Is there anything known about it? Because you talk about polarization,
Yeah.
is there really something known about this background component in a polarization?
There would only be the limits from it's not showing up in WMAP and Planck. But we don't really have polarization measurements at the gigahertz or megahertz frequencies on large scales.
I'm just curious, how high do you have to fly the balloon?
Balloons go to 120,000 feet, and that's so that's high enough to get above all the atmospheric emission for these purposes. And it's also just the general height of scientific ballooning. They sort of have a region where you have to go to.
Is there any emission associated with that you have to worry about?
With the atmosphere?
Well, just outside the instrument.
So you're above almost all of the atmosphere is so thin at that point that emission from the atmosphere is negligible.
And the balloon has no.
And the balloon. So to get technical about it, you saw how long the train was there from the balloon to the instrument. So the balloon covers a tiny portion of the solid angle seen from the instrument. And then if you noticed, the horns are not pointing straight up, but they're kind of doing this. So they're it's in the far side lobes of the horns. So, and then even furthermore, there's actually kind of above it, there's a little reflector shield thing that sort of blocks the balloon, and that we can adjust the temperature up and down and see if there's any response in the radiometers, and there's none because it's way side lobe.
So now that you've made the measurement and,
Yeah.
and excited the theorists, I'm sure they'll be able to entertain themselves for years. Do you have any plans for the instrument after this?
So our arcade probably not, because this is pretty much the measurement you can do with that. I've been talking with some of the people at NRAO about another measurement at the megahertz frequencies, another absolutely calibrated measurement at the megahertz frequencies, because any of these things from the ground do have uncertainties with the atmospheric pickup and ground pickup and all that kind of stuff. And so to do in the past, Haslam and things like that, the goal was never to get an absolute calibration. That was just something they did, kind of as an afterthought almost. So to actually do a megahertz radio map with absolute calibration would be a new thing. And I think there's another.
Pursuing the idea of a local origin.
Yeah.
Yeah, very strong limits against variability.
In time,
Yes.
I would say there's extremely weak limits on that. Yeah. These measurements are made at different frequencies, decades apart.
Yes, I'm wondering about the population tree source counts. So what kind of, because you said like the source counts are basically at too high resolutions, what you're saying, to pick that kind of fluctuations up. So you need like lower resolution source counts, basically, is what you're saying. And what kind
You
of,
would need, I wouldn't call it source counts at that point. It would be like low resolution interferometer maps.
yeah, what's
But
the resolution to target this kind of like, for example, population 3 supernova things?
let's see. You would need to be at these angular scales. So if you can go from L to angular scales in your head, you need to be at these angular scales. But the problem is for interferometers, that means larger baseline, right?
Right, but that seems to be on the scales where actually you can do measurements, because if you have, for example, VLA in a compact configuration, you have that. If you also have the,
So VLA and compact, what's the?
for example, then go to 1 gigahertz and then go to the height. So that gets you in that range roughly.
Is that right? Because I would be interested if this could be done, interferometry, yeah.
You can subtract the others, because the problem is then you hit confusion immediately.
Right.
But the good thing is you can also then have the higher resolution, so you can remove all the compact sources from higher resolution data to have a kind of like a diffuse source. Kind of.
That would probably be a pretty good EVLA proposal. Maybe.
One more.
Have you looked at anything other than Monopole in your data?
No, and that's good. So you can calculate what the dipole ought to be, right? And if it's extragalactic or cosmological, you should see the dipole and it should align with the CMB dipole. Yeah, it's too small to see in the gigahertz stuff. If you made a dedicated experiment to do it in megahertz, you could probably do it. And that was actually one of the motivations for doing another measurement in the megahertz range with an eye toward a real absolute calibration. Yeah. So the dipole would be a smoking gun of extragalactic or cosmological origin if it aligned with the CMB dipole. If it didn't, that would be strange.
Okay, well, Jack will be here through tomorrow till about 3 p.m. And please let us know if you'd like to join us for dinner. And let's thank speaker again.